All right. Hello. Check how many persons are there.
All of them have left. One person. One person. How is you? Is you? Someone saying you're fine.
Okay. Okay. All right. Are you there now? So please, if you are there, say hi. Say hi. I should move on. So we're resetting. Let's see. Let's see. How many persons now? One. Please, if you're already there, can you just share the link? Okay, please, those of you that are there now, share the link. Please. I've tried to use a different phone and see where the problem is coming from. So share the link with others. Share the link. Thank you. I think it's okay now, right? All right, all right, all right, all right, all right. Share the link, please. So sorry, try to inform others. Tell them that it is working. It is working because this is actually our exam preparation. So it's supposed to hold. It needs to hold. So share the link. Like the video, invite. I have 6 watching. Once it's 10, I'll start quickly. Once we have 10 persons, I would start. I have 6 persons watching now. Now we want to look at optics, and I'll be starting from refraction. Refraction. Tell others that we have started, and it's 6. So tell them we have started. Let's see. Okay. I believe 5 persons. I believe you're sharing it. All right. So now let me move on. So
That's fine.
So, my God, even network, everything is trying to work against this. So it actually means that what I want to unravel, the concept I want to teach will be very important for your exams. I believe that is why all these distractions are coming in. So, but to see to it that we really work on this revision, it's very important. How many persons are live now? 6 persons. 6 persons. Should I continue with the 6 of you? Still 6? Okay. Now let's move on. I want to look at refraction at plane surface. Refraction at plane surface. Now, when you talk about refraction, remember this is a revision class, so I'll be going straight to the point so that we can do at least in a few minutes, and then we call it a day. Now, when you talk about refraction, refraction, you should know, is not the same as reflection. So in our last class, we considered reflection. In this class, we're going to consider refraction, right? So when you talk about refraction, refraction is the bending of light as it crosses the boundary between two different media. Refraction is the bending of light as it crosses the boundary between different media. A good place you can observe the phenomenon of refraction is water. If you bring spoon and immerse in water, you will notice that when the spoon gets into the water, it will bend. So that bending, it looks like the spoon is now bent while under the water. That bending is what you call refraction, right? So that is refraction. Now, light can travel from a less dense medium into a denser medium, or light can travel from a denser medium to a less dense medium. So we want to consider refraction when light travels from less dense. Less dense can also be called rare medium. So when you see rare, it means less dense to a denser medium. Now, when light travels from a less dense medium to denser medium, the refracted ray always bends towards the normal. Take note. Exam would ask you this. Which of the following is correct when light travels from a less dense medium to a denser medium? What do we mean by this? For example, when light travels from air to glass, it simply means it is traveling from less dense to a denser medium. So you take note that when light travels from less dense to a denser medium, the refracted ray bends towards the normal. Remember, this straight line stands for our normal, right? So you should take note of this. And in this case, we can get what we know as angle of deviation. So if I continue this incident ray, if I project it further, now you now see that this angle, this extra angle, is what you call angle of deviation. So the angle of deviation is the amount by which the incident ray shifts from the normal path. The angle of deviation is the amount by which the incident ray shifts or deviates from the normal path. So this is the normal path it is supposed to follow, but it eventually bends. So that amount of shift or deviation is what you call angle of deviation. Now, how do we find angle of deviation from less dense to a denser medium? Very simple. Very quickly, you will notice that this angle of incidence, is equal to this whole angle. Both of them are vertically opposite angles. So I can say that delta plus r is equal to I. So that delta becomes I minus r. So this is how you can find angle of deviation when light moves from less dense to denser. So very quickly, number 2, we want to consider when light travels from denser to less dense. When light moves from a denser medium to a less dense medium, for example, when light travels from glass to air, it means it is traveling from less dense to denser medium, from glass to air. So this is our angle of incidence. When light travels from a denser medium to a less dense medium, the refracted ray bends away from the normal. It bends away from the normal. So this is very important. While in this first case, it bends towards the normal. So please take note of this. Now, for this case, you have something like this. Bends away from the normal, and this is our angle of refraction. Then what will our angle of deviation be? If I continue the incident ray like this, then it means that this is my angle of deviation. So for this case, our angle of deviation is going to be delta equals r minus I. So take note of the two relationships. Now, very quickly, I want to move on. Please take note of these two relationships, from less dense medium to a denser medium, and then from a denser medium to less dense medium. The formulas for finding angle of deviation is this. and this. Let me give you a quick example to dissect this for you. Let me write it. Light travels from water of index 1.33 to air of index 1.00. Find the angle of deviation if I equals 30 degree. If I equals 30 degree. So find the angle of deviation. So we're going to solve this very quickly. We're going to solve this, even though we have not really gotten to Snell's law, but let's quickly use it because I believe you know it. This is a revision class. Meanwhile, do well to hit the like button. I'm so sorry for the disappointment. I had to get a different phone so that this can still hold. And meanwhile, I'm still going to have another session, hopefully tomorrow, but I'll let you know so that we can now do this when everybody is settled. So do well to hit the subscribe button. How many persons are live now? 6 persons. Wow, 6 persons. We need more people online. We need more persons online. Quickly share the video. Now let's solve this. This time around, we are moving from water. This is actually the refractive index, 1.33, and the refractive index of air is 1.00. So the value simply tells you that water is denser than air. So we are moving from denser medium to a less dense medium. Denser medium to a less dense medium. So quickly, this is the diagram. This incident, which is 30 degree. Then this is what we have. So we need to find our angle of refraction first before we can find deviation. Remember the refractive index here is 1.33 and that here is 1.00. Now you should know that Snell's law can be written like N1 sine theta 1 equals N2 sine theta 2, right? N1 means refractive index in the first place. So refractive index in the first place is 1.33. Let's get calculator. Then sine theta 1, which is 30 degree. Then refractive index in the second place is 1.00. Then sine theta 2, which is actually the angle of refraction. So very quickly, I would have that sine r, if I make this the subject, is going to give me 1.33 sine 30. So that sine r is going to be, let's do it, sine 30 times this. Sine 30 is 0.5 times 1.33. Okay, 0.5 times 1.33. So this will give me 0.665. So this is what I have. Then r becomes sine inverse 0.665. So let's find our r. Our r is going to be so somebody should punch. My phone is just hanging, so just finding a way to delay us. Okay, so sine inverse. How many persons do we have present?
Another name for denser medium.
Okay, another name for denser medium.
Another person say 1.7 answer.
4. Okay, let's see.
1.7 degree.
So sine inverse of 0.665. I have.
Someone say 4.6.
Okay, I have 41. Who got this? 41.68.
Yeah, Chukwuemeka John.
So Chukwuemeka John Paul. Thank you, John Paul. I love your spirit of consistency. Always in the class. I love that. And I really appreciate that, John Paul Chukwuemeka. always in all the classes. So the angle of refraction is
Jesus, is he?
41.68.
No.
So the next
41.6. That is
41.68 is our angle of refraction from what I've evaluated. Now, but the question is asking for angle of deviation, remember. Now, when you're moving from a denser medium to a less dense medium, what is the formula for our angle of deviation? Our angle of deviation is going to be r minus I. You don't even need a soothsayer to tell you. Now, you notice that your r is bigger than your I, which is 30. So you should know you're removing 30 from this. So this is the formula, r minus I. So I would have 41.68 minus 30. And this would give me 11.68, I guess. So when you subtract, so this is what we should have. So who got the answer? Anybody? Anybody?
which answer again?
Who got this final answer? Anybody?
Nope.
All right. Now let's quickly move on because I will soon tidy up since we are not much. How many are there now?
Okay, someone wrote Anthony Nwankwo.
Anthony,
11.7 though.
thank you. Approximately correct. How many persons are present now?
It was 10 before, but it's 9 now.
Okay, that is good. It means there is a let's move on. So do well to screenshot so that I can always be fast. Now, we have the next thing we want to look at is law of reflection. Laws of refraction, refraction. Laws of refraction. We have two laws of refraction. Remember, when we studied reflection, we considered that there are two laws of reflection, right? If you recall, we said the laws of reflection are two. In same way, the laws of refraction are also two. So number one of the laws of refraction is known as Snell's law. It's known as Snell's law. And what is Snell's law? Snell's law simply says that the ratio of the sine of angle of incident to the sine of angle of refraction is a constant. I repeat, the ratio of the sine of angle of incident to the sine of angle of refraction is a constant. And this constant is known as what? Refractive index. So that is Snell's law. Mathematically, you can just say at n is equal to sine I over sine r. So this is the first law or one of the laws of refraction, which is known as what? Snell's law of refraction. So I believe you are familiar with this, right? Yes. Now the second one says that the incident ray, the refracted ray, and the normal at the point of incidence lie on the same plane. I repeat, the incident ray, the refracted ray, and the normal at the point of incidence lie on the same plane. So that is the second law of refraction. Remember, there's no point writing it. That is just a law we just stated, which you should know. Now, one of the things you should understand is that refractive index is a constant, and the refractive index is a constant. And we can define the refractive index in about 4 different formulas. So we have about 4 different formulas for refractive index. Take note that this is first formula for refractive index. So it means that you can find the refractive index from Snell's law. Now, what would the exam ask you? Exam would ask you which of the following relations does not define refractive index. You should know that this relation defines refractive index. Sine I over sine r defines refractive index. I want to give you 3 more formulas that defines refractive index. Number 2 is that refractive index can be defined as the ratio of speed of light in air to the speed of light in a material medium. So refractive index is speed speed in air, speed of light in air to speed in a material, in any material medium, say in water, say in glass. That is what we mean by material. So you can say that refractive index is speed in air over speed in glass. You can say the speed in air over speed in water. That's what material medium means. So, and I'll denote that like this: C over V, where C is speed of light in air, and then V is speed in a material medium. So this is second formula that defines refractive index. Now, number 3 formula that defines refractive index can be gotten from here. Now, one of the things you should know is that when light travels from one medium to another medium, the speed of that light will change. The wavelength of that light will change, but the frequency remains constant. Exam would ask you, which of the following quantities remains constant when light travels from one medium to another medium? The quantity that remains constant is what? Frequency. Frequency. So when light moves from, let's say, air into water, the speed would change, the wavelength would change, the frequency remains what? Constant. Take note of this point. So if we know that frequency remains constant, you can recall that speed is actually f lambda. So I would say speed lambda, wavelength in air, because frequency is constant. So I'm not saying frequency in air because it's the same, over, I would still say f times wavelength in a material. And then refractive index becomes wavelength in air over wavelength in a material. This is the third way of defining refractive index. Number 1 is from Snell's law. Number 2 is this C over V. Number 3 is in terms of wavelength. And the fourth one, can you guess the fourth one? If you know it, drop your answer in the comments. The fourth one, the fourth way of defining refractive index. Tell me quickly if you know, because we are preparing for exam. Any answer? Any answer? Any answer? You know the fourth way of defining refractive index. Tell me, how many persons are live now?
11.
11. How many likes? So please hit the like button if you are there. So sorry for delaying you, but thank you for having a strong spirit. A lot of you have strong spirits that still kept you waiting for this video. And I really appreciate your consistency, your support for Prime Concept Academy. I really appreciate. And I promise you that you would not be disappointed at the end. Now, quickly, the fourth way of defining refractive index is in terms of real and apparent depth. Real and apparent depth. That is the fourth way of defining refractive index. So what it means is that refractive index is actually the ratio of real depth to what now? Apparent depth. Apparent depth. So this is the fourth way of defining refractive index. Real depth over apparent depth. So I've given you 4 relationships for refractive index. The first is from Snell's law. The second is in terms of speed. The third is in terms of wavelength. The fourth is in terms of real and apparent depth. So screenshot this. I want to rub it. So very quickly, I want to also inform you that this is actually the formula for Snell's law, which we can still write in another form, which is more important to me. I even prefer this next form to this one because it's easier to solve problems with it. Now you can write Snell's law like this. You can say it is N1 sine theta 1, if you like, or you can say sine I equals N2 sine theta 2, if you like, or you can say sine R. So this is another way of representing Snell's law that is going to be useful to us, right? Resolving problems from here. Now let's take one problem before we move on, because I've tried to summarize this to a great extent. So let's take a problem. How many persons are alive now? How many? 10. All right, let's take this problem.
11.
Okay. Remember, exam. Now, I want to quickly use this medium to encourage you that irrespective of the rumors about strike, ASU strike, do well to keep preparing for your exams. So don't take chances and say your exams may not hold. Now, even if your exam happen not to hold tomorrow, for those that will be writing tomorrow, if it happens not to hold tomorrow, the strike may be called off overnight and your exam will be fixed overnight. And at that point, some of you may be caught all of a sudden. So please do well to prepare as if you are writing it tomorrow. Even if it doesn't hold tomorrow, it won't be far from tomorrow, that exam will hold. So please do well to prepare. Now we have this question. A ray of light is incident on the surface of water at an angle of 30 degrees. Calculate the... Okay, we've solved something related to this already. Okay, we've solved this already, so let me leave it. We've solved this. I already gave this for deviation. So let's do this one. Let's on this. So let's pick on this quickly. The difference between the apparent and real depths of a swimming pool filled with water is 1.5 meters. Calculate the depth of the swimming pool if the refractive index of water is 1.33. So we're going to solve this together. So how many persons are there? All right. So we're going to solve this together. Now I'm going to solve without wasting time. So the question says the difference between the apparent and real depth of a swimming pool filled with water is 1.5. Now, one of the things you should know is that real depth is always greater than apparent depth. So if they say the difference between apparent and real depth, it simply means real depth, which is greater, minus apparent depth, which is smaller. So the difference between this, they told us, is 1.5. So that is what I've done. Now they say calculate the depth. When they say the depth of the swimming pool, they are talking about the real depth, because real depth is the actual depth of the swimming pool. But apparent depth is the depth that your eye perceives, and it is due to refraction. Exam can also ask you, apparent depth occurs as a result of A, refraction, B, reflection, C, diffraction, and D, interference. So you should know apparent depth is perceived as a result of refraction, which is what we are studying. So they said calculate the depth of the swimming pool, which is R. So we're looking for R. Now they gave us refractive index of water as 1.33. Now we know that refractive index can be defined in terms of real and apparent depth. So we can use that idea to solve. Now we know that refractive index n is real depth r over apparent depth. So what it means is that from this first equation, I'll try to make apparent depth the subject. If I make A the subject from this first one, let's call this 1, call this 2. From equation 1, I would make A the subject. So I would have that A would be R minus 1.5. What I've just done is that I moved 1.5 to this side and I moved A to that side so that R minus 1.5 would be equal to A, which is what I've written like this. So I then have that my refractive index is 1.33. Then I have the real depth R, which is unknown. Then instead of writing A, I'm then going to write R minus 1.5. So this is what I have. So I'm trying to find R, I can cross multiply. So I'll have 1.33, which is this, into R minus 1.5, which is equal to R. So this by this would give me 1.33 R minus this by this would give me, let's multiply, 1.33 times 1.5. How many persons are there? I hope you are following me. How many persons are there now? So equals R. So quickly I have 1.33 R. When this R crosses, I have minus R equals, when this one goes, it becomes 1.995, right? Yes. So that if I subtract, this is 1.33 R minus 1 R. So that is actually going to be 0.33 R equals 1.995, and R becomes 1.995 by 0.33. So if I divide this would give me 6.05 meters, and that is the real depth of the swimming pool, 6.05 meters. So I believe this concept is clear to you. So quickly screenshot this so that we can see how to conclude on this part. So I would like to leave lenses for another class because lenses is very important to me. So but let's conclude on plane refraction at plane surfaces, right? So we still have
6.045.
Thank you. Who is that person?
Anthony Nwankwo.
Anthony Nwankwo, thank you. You are very correct. So it means you got the answer before I finished. Any other answer?
No.
All right. Thank you, Anthony. Now let's move on. So we want to look at what we know as optical invariant, which always comes out in exam. Optical invariant. What is optical invariant? Optical invariant is a mathematical equation that gives the relationship between various optical parameters. Optical invariant is a mathematical equation that gives relationship between several optical parameters. When you say optical parameters, it includes angle of incidence, angle of refraction, refractive index. These are optical parameters. So a formula that combines so many optical parameters, say refractive index, say angle of refraction in one medium, in another medium, in another medium, that equation is known as optical invariance. Now let me make it clear to you. Now say we have a 3-medium boundary. I will have something like this. Let's say this place is air, and this place is, let's say, water, and this place is glass, and this place is air again. So you see that we have 3 interfaces. We have air to water, we have water to glass, and we have glass to air. So we have 3 interfaces. So a mathematical formula that can interrelate all these things is what you call optical invariant. This particular question, I'm assuring you that it comes out almost every year. So take it very serious, and it's very simple. Now, if you draw your normal here, and this is your incident ray, therefore this is your angle of incidence. When this moves from air to water, it would refract. So you would have R1, the first angle of refraction. Now, this your refracted ray, when it hits this place, this refracted ray behaves like incident ray to this particular medium. So it means I can draw a normal here. This particular refracted ray is now an incident ray, right? But one of the things you know is that if this place is R1, this place should also be R1, which from mathematics they are called alternate angles, and alternate angles are equal. So now when this enters and hits here, it will do what again? It would refract. So you get R2, your second refraction. Now this second refraction, when it comes here, it begins to act like incident again, so that you can now get finally this one, which is your emergent, right? Yes, so this system is an optical invariant system. And what is the formula that connects them? The formula is n sine theta is equal to constant. So this is actually what you know as optical invariant relation, which we can expand on this by just saying that you have n1 sine theta 1 equals n2 sine theta 2. You can still say equals n3 sine theta 3, and so on. Now let's relate it to what we have here. Remember, this is air, so I would say n air, I would say n water, I would say n glass. So if we relate this to this, applying from this to this, I would have n1 in this place is actually n air, sine theta 1, the angle in this place is I, equals the angle in the refractive index in this second place is nw, and the angle in this place is sine r1. So I have this first formula. I can combine water and glass. So if I'm combining water and glass, it means I'm having n water, then sine r1, which is this angle, equals, I'm in glass now, n glass, then I have sine r2, which is this. Remember, this place is also r2. This other angle is also r2. This place is r2, right? Because they are still alternate angles. So with these two relations, I can solve problems. So let me give an exam fast question under this quickly. So how many persons are there?
Yeah.
So how many likes? Please hit the like button. Hit the like button to quickly notify others that we are here, because we have one more important thing to handle, which is real and apparent depth. The concept of real and apparent depth. Now let's take this example. Okay, let me rub this side. Let's rub this. So we have this question that came out in an exam past question. They said in air, water, glass, parallel sided media, calculate the angles of refraction R1 and R2. If N water is 1.33, N glass is 1.5, N air is 1.00, and the incident angle is 30 degrees. So this is what we have. So I'll give you 30 seconds to attempt it. John Paul, I'm also counting on you. Chukwuemeka, then I think 1 4, counting on you, and others which have not seen your name yet. So I'm counting on you. Quickly solve this. 30 seconds. Let's see how fast you can produce the answer. Giving you 30 seconds. Any answer yet? Okay. 15 more seconds. 15 more seconds. 5 more seconds. 3 more seconds. Any answer? All right, I think I should solve now. And let's solve it. It says in air, water, glass. It means you are moving from air to water, from water to glass, then from glass back to air. Parallel-sided media. Calculate the angles of refraction R1 and R2. From the diagram, you can see where we labeled R1 and where we labeled R2. So that is very clear. So we have from air, I would have N air sine I equals N water. Remember, it's from air to water. So equals N water sine R1. Because that is the first angle of refraction. So let's substitute. N air is 1 times sine 30. I is 30. Equals N water is 1.33 sine R1. So that if I make this, I'll just have sine R1 equals 1 times sine 30 divided by 1.33. So this will give me, I'll quickly punch, sine 30 0.5.
Okay, so yeah, Anthony.
Divided by,
Anthony.
Do we have an answer? Anthony, what's your answer?
R1 22 degree.
Okay, Anthony said R1 22 degree. R2, do you have an answer? Is there any answer for that? So it means that this is what I have. Then it means that R1 is sine inverse of 0.3759, right? So
So Zebelun. Z22.
22. Okay, same. You agree with him. Okay, any other answer? All right, let me evaluate. So sine inverse of 0.3759. So 22. So I believe you got it. 22 degree approximately. So this is what we have. So the next thing is for us to find R2.
Okay, R2.
R2 by
Anthony
who?
Nwankwo.
Anthony, okay.
19.5 degrees.
19.5. Any other one? Okay. Now, please screenshot this. I want to rub this part so that I can resolve on this space. So screenshot it. Screenshot it. If you are okay, tell me to rub. Say rub so that I can rub it. Or say move. Move on. I can move. How many persons are there now? Okay. Now, I think I can rub this space and solve. So we want to find R2. So this time we are moving from water to glass. Remember, we have moved from air to water. So we want to move from water to glass. So I have N water sine R1, which is in water, equals N glass sine R2, which is now in glass. So N water is 1.33 times sine R1, which we got as 22, equals NG 1.5 sine R2. So that if I solve, I'll have that sine R2 would be 1.33 times sine 22, right? Divided by 1.5. So if I punch this, I have, it's going to give me 0.5 by this. So 1.33 times sine 22 divided by 1.5. So I have 0.3 3, 2, 2. I sine R2. Then R2 becomes sine inverse of 0.3322. So let's quickly do it. Sine inverse of 0.3322. So thank you, 19.4 approximately. So I believe this is also correct. Who got it actually? Nwankwo.
Anthony Nwankwo.
Anthony, you are correct. Thanks. This is R2. So the final thing I want to do, remember I'm going to push lenses because it's important. So in my next live schedule, looking at lenses, I'll be looking at waves at the same time. There are a lot to learn under waves. So do well to hit the subscribe button. If you are watching and you are yet to subscribe, hit the subscribe button so that you'll be notified on when we'll be handling waves and then lenses. It's very important. So the last thing I want to look at for today's class is what we know as critical angle. Critical angle and total internal reflection, not refraction. Total internal reflection. So we want to look at it now. First, we want to explain critical angle because it is a criteria for you to learn total internal reflection. So what is critical angle? Critical angle is the angle of incidence in the denser medium when the angle of refraction in the less dense medium is 90. Critical angle is the angle of incidence in the denser medium when the angle of refraction in the less dense medium is what? 90 degrees. So that is critical angle. Now say we have a diagram like this, and this is dense. Remember, for you to talk about critical angle, it has to be from a denser medium to less dense. So you can never talk about critical angle moving from less dense to denser. You can never experience the concept of critical angle. So it can only be experienced from denser to less dense. So what is critical angle? This angle, which is actually called angle of incidence, the new name becomes critical when your angle of refraction here is 90 degrees. So you no longer call this incident angle, you now call it critical, as long as this is 90. If this is not 90, any other value this takes, this retains the name incident angle. But provided this is 90, this becomes critical angle. What is the formula for critical angle? Is what you know. Sine C is 1 over n. But I don't really like to use this. I prefer to use the normal relation n1 sine theta 1 equals n2 sine theta 2. This is correct. Why I prefer this is because this refractive index n is actually a relative refractive index, which I don't want to really go into. That's why this would be easier for us to use. So whenever you have problems like this, you can use this formula. Say I want to apply this second formula for the critical relation. So I have my refractive index here is n1, so I can call it n1 sine theta 1 is c, then n2 sine my theta 2 is 90. So I would have that n1 sine c equals n2 sine 90 is 1. So 1 times n2 is n2. So you can say that sine c is n2 over n1. So this formula and this are actually the same thing. So what it actually means is that n is equal to n1 over n2. That is what it means. N is actually n1 over n2. So you take notes of that. I will give an example that will help you understand how to use this. But very quickly screenshot this so I can rub and give an example from it. So this is where we're going to draw it. So when we take this example, we look at total internal reflection, which does not have calculation, and we will be done. So let's take this example. Calculate the critical angle at a glass water interface if the refractive indexes of glass and water are 1.5 and 1.33 respectively. So I'm giving you 30 seconds to solve because we are almost done. So let's have a little time for you to solve this. 30 seconds to solve so that I can now conclude. 30 seconds, I'm waiting. 30 seconds. So look at it, see how to apply the formula I just gave and solve it. So how many persons do we have now? 6. Okay. Any answer? All right, let me solve and save the time. Now we have critical angle. Okay, calculate the critical angle at a glass water interface. We're looking for C, which is very obvious, at a glass water interface. So we're moving from glass, which is denser, to water. So N for glass is 1.5.
Okay, yeah.
N for water is 1.33.
Someone, come on.
All right, who has an answer?
2 people.
Okay.
Anthony,
What do you have?
62.46 degrees.
62.46. Let me write it here. 62.46. Anthony, thank you. Who else?
Chukwemeka John Paul
John Paul.
62.4.
0.4, same answer. Okay, now let's verify. Let's solve. So, I told you that you can use the formula. N1 sine theta 1 equals N2
Another
sine
person
theta
said the answer.
2.
Another person answered Agatha.
Agatha, the
NECO
first
or by
lady. The answer is what?
62.4.
Okay, similar. All right, let's verify. Now we have N1, remember from glass, so N1 is 1.5. Sine theta 1 is C, equals N2 is water, 1.33. Sine theta 2 is 90, actually, always 90. So I want to find this. So I have that sine C is 1.33 times 1, sine 90 is 1, divided by 1.5. So if I do this, I would get 1.33 divided by 1.5. So this is 0.86, okay, 8867. So this is what I have. So that C becomes sine inverse 0.8867. So let me quickly do that. 0.8867. So this will give me 62.46 degrees. So this is correct. This is also correct. Just approximation difference. So thank you, Jean Paul. Thank you, Mark. Thank you, Agatha. Yes, Anthony. Thank you. Your answer is correct. So it means that even with the disruptions, you are still really understanding me and following this very clearly. Thanks for understanding what we are doing. So finally, is total internal reflection. Now, what is total internal reflection? Total internal reflection is the bouncing back of all the incident ray to the same medium from which it was incident. Now, when you have a surface like this, and you're moving from denser medium to less dense, it has to be from denser to less dense before you can experience total internal reflection. So let me give you conditions. Conditions for total internal reflection. 1, light should travel from denser to less dense. That is the first condition. Number 2 condition is that critical angle should be greater. Critical angle, let me use this term, should be exceeded. Critical angle should be what? Exceeded, or you can still say the angle of incidence should be greater than critical angle. Or you say critical angle should be exceeded. It means your incident angle should be bigger than your critical angle. So these are conditions for total internal reflection to occur. Now, what is total internal reflection? If you are flashing light on a surface, there's going to be refraction, right? Part of that light would come to this place and bend. Now, and some of them would be coming to this place, coming back to the same medium. But what is coming back here is faint. Most of them is still here as refracted ray, while a few of it is just here. Now, you keep increasing this incident angle. When you keep increasing it, you increase it to a point where it becomes greater than the critical angle. When it becomes greater than the critical angle, you will no longer have any ray here. By that time, everything would now be bounced back to this point. So that point that is attained, where all the incident ray return back to the same medium from which it was incident, that phenomenon is what you know as total internal reflection. It is the bouncing back of all the incident ray to the same medium from which it was incident. And it occurs under 2 conditions, which is when light travels from a denser medium to less dense, and when the critical angle is exceeded. So these are the things you need to know for refraction at plane surfaces. We have established a good number of points in this video. We've talked about refraction, what refraction actually is. We looked at refraction from less dense to denser. We considered refraction from denser to less dense. We looked at angle of deviation and how to find it. We looked at laws of refraction. We said there are 2 laws of refraction, Snell's law and the other law, which does not really have a name. Then we also mentioned that you can define refractive index in 4 ways. We defined refractive index in terms of Snell's law. We defined refractive index in terms of speed of light. We defined refractive index in terms of wavelength of light. We defined refractive index in terms of real and apparent depth. Then we mentioned that frequency is always constant when light travels from one medium to another. We looked at this. We looked at optical invariant. And then finally, we concluded with critical angle and total internal reflection. So I believe that within this short time, we have been able to achieve a whole lot. But trust me, we are going to achieve much more in our next live session, which I'll be communicating with you on the community platform broadcast and on my WhatsApp platform. For those of you that are on my WhatsApp platform, I will share the information with you. But please do accept my sincere apology for the breaks we had in this video. Trust me, the next time we'll be meeting, it won't be like this. I'll try to put everything in order before that time. So please let me give a shout out to my top fans that remained till the end. So tell me those that are still present. Huh?
I can't tell.
All right. So then those of you that remain, but how many persons are still present?
Okay. Let me name them.
All right.
Anthony Nwankwo.
Anthony, congratulations. Congratulations.
Chisom.
Chike Chisom,
Chukwuemeka
congratulations.
John Paul.
Chukwuemeka John Paul, always consistent. I need to see you.
Zebulon
Chukwuemeka John Paul,
Enoch.
congratulations. Who?
Zebulon Enoch.
Zebulon, congratulations.
Vintage.
Vintage, congrats.
Agatha Neka.
Agatha, congrats. NECO. Thank you. Thanks for staying till this point. So please, I want you to do one thing for me. Immediately after this live session, comment on the video and then share with all your different platforms. Tell them that Prime Concept unraveled the concept of optics, and we'll be having another live session which will be communicated to you. Thanks for always supporting this channel. This is Prime Concept. Thank you.